Welcome to the show today, Green Spring. Thank you for tuning in. I'm proud to welcome our resident cosmologist, Richard Schmidt, who runs the cosmology group here at Green Spring. We've got a few updates for you about some satellites floating around in space and some rovers. And then we're going to talk a little bit about gravity, the thing that keeps us all down to earth, I guess, so to speak, right? So
Good
thanks
pun.
for coming. It's certainly keeping us sitting in our chairs right now. So Richard, thanks for coming on the show. A few things to update folks on since we last talked is, I think, two pieces. The Curiosity rover currently exploring Mars, which I think people are saying is on borrowed time, right? It was only
That's how I
supposed to
look at
last.
it. And they have a energy source on there that is nuclear. And it was designed for 2 years, and they've already passed 2 years.
Yeah.
So that's why I say it's on borrowed time.
So really they're just expecting it to die at any moment now?
Nobody has said anything.
Yeah.
You know, they're very quiet about that issue.
I guess they're happy to get anything out of it.
Oh, yeah. You get as much as you can get out of it. Yeah.
Now, is it still moving backwards? There was something about it hit a rock or something and a gear on it broke.
They have some close-up pictures of the wheel showing a hole in the wheel. It actually punctured a hole, yeah. And so it's been dented, but the little ridges in the wheel that grab onto the surface to give them traction, those ribs are still there.
That's good.
So they haven't lost their ribs.
And did the rover complete its objective? It was making its way, I guess, up a mountain on Mars, right?
Well, it hasn't gone up very far at all. It's been down in the crater, and it traveled along the crater, which is a flat plain.
And there's the rover right now, in case people are wondering.
And it got to the foothills, you know, the bottom of the mountain. Mount Sharp is what they call it. And they want to travel up it. But they're finding such interesting information down below.
Right.
They spent all their 2 years just looking down on that, and they found good stuff. You know?
And the things that I'm even trying to refresh the show that we did maybe a year or two ago. The things that they found on Mars from the Curiosity, what did that help them understand about Mars? It was something about water.
Yeah, well, the whole purpose of going there is to find out, was there ever life there on Mars? If there was life, would evidence of that life be sustained? Would it be destroyed over time? Or could it live right up till now so that we could see something about life, evidence of life? And so they went through and they said, well, we found evidence of water. And so that's part of life. As we know it, we need water. And seeing water did flow freely on Mars is something very important to finding life. And then they found nitrogen, which is an element used in life. And they found minerals that would sustain life. So they find a lot of good stuff that says, hey, yeah, life could have been here. Now the question is, was there life? They've seen some methane coming out of the surface. Where it came from, they're not sure. Did it come from life living right now? Or did it come from nitrogen that was stored away and then came out because of the surface cracks? You know?
There are a lot of living creatures on Earth that produce methane gas. So I guess that's what they're wondering. Not that they think there's any four-legged mammals walking around on Mars. I think the life they're talking about is at a very molecular basis, correct?
Any kind of life. They're just trying to find out, has life evolved elsewhere in the universe?
Yeah.
And getting further out than the solar system is pretty hard. So we're taking a look right next door neighborhood, and Mars is the closest guy, so we looked up on Mars.
Yeah, he is the closest guy, but we do have, it's a very exciting time right now for NASA because we do have a probe reaching the outer end of our solar system.
Much further out, yes.
Much further out. And I remember taking my astronomy class in college back in 2007 and learning about the New Horizons probe and exploring the Kuiper Belt and Pluto and some of the new dwarf planets. And thinking, gosh, I can't wait till it's 7 or 8 years from now. I can just finally see what's out there.
Time
and
has
this
come.
week is exciting because the New Horizons is finally reaching Pluto.
Right.
And there's a lot of things that went into what makes Pluto a non-planet now, but a lot of those things are finally getting photographed, and we have some of the first pictures of Pluto coming out this week, and it's very exciting. But I think before we talk about the New Horizons, why don't you explain that part of the solar system that it's exploring? Because this was just discovered maybe 7 or 8 years ago when the dwarf planets and becoming Kuiper Belt objects give them a lowdown of that neighborhood of the solar system and what's going on out there.
Okay, you know, if the audience is familiar with the solar system, New Horizons spaceship went out past Mars, past Jupiter, past Saturn, past Uranus, past Neptune. Now, Neptune is the last planet as we recognize them now. And Pluto gets actually inside the orbit of Neptune for a little bit.
Right.
Most of the time it's way outside of that. And after Pluto does come the Kuiper Belt. Now you could say the Kuiper Belt is all the way into Pluto, or you can say you really don't get into it till you pass Pluto. Now you're getting into the Kuiper Belt, which is a whole bunch of like asteroids.
Right.
Just floating around out there, many, many of them, held in place by the gravity of the sun.
Yeah.
The sun is holding that cloud of asteroids out there. They could have formed a planet, but they didn't.
They sort of crashed together at one point and turned into another asteroid field. The way I kind of imagine it in my head is, you know, we have the sun at the middle, and then we work our way out from there with the solid planets, ending with Mars, I believe. Then
Mars
there's an
is
asteroid.
the last solid planet.
Then there's an asteroid belt. Everything after the asteroid belt is the gas planets. And then following the gas planets, more or less gas.
Pluto is not a gas planet.
It's an ice planet, right?
Pluto is a solid planet. Yeah.
He is a Kuiper Belt object, right? Not necessarily a planet.
Okay, you could say it's a
But
Kuiper
either
Belt
way,
object.
you get the gas planets. Following that, then it's another field of asteroids. That's the Kuiper Belt.
Yes.
And that's what Pluto is a part of, as well as Eris and a few other, what's the other names of some of those smaller planets that they say is out there? One's called Make, I believe. They've got all sorts of wacky names.
No, I haven't been looking
And
into that.
they've named them all sorts of things. So I think in further understanding that part of the solar system, that is what this probe is doing.
Yeah, this probe is going so fast that it cannot land on Pluto. It would just smash. So as it passes by, it's only got a few hours to look at Pluto.
Right.
And as it looks at Pluto, it's going to be taking images, but it's also going to be examining the atmosphere of Pluto. It'll be looking at Charon, the closest moon to Pluto. And then after it passes Pluto, it's going into the Kuiper Belt looking for other dwarf planets.
Okay.
So if it can find some other big ones, fine. If it finds small ones, that's okay too. They want to find out more about the Kuiper Belt.
Right.
And so that probe will do it.
That's good.
Now they're talking about this power source going bad. I don't know what they're going to do when they get out there. They must be reserving enough power to send back some data. Otherwise, why bother having it go out
Well,
there?
we're already getting some of the first pictures back from the New Horizons, and that's been pretty exciting. I think from now until next Tuesday, it's going to be beaming back Pluto pictures. Is that correct?
Yeah, it's going to concentrate on Pluto.
Concentrate on Pluto. And what is the end game for this probe? Are they just expecting it to fly into the Kuiper Belt and send some pictures back, and then eventually it'll crash into something, and that's the end? Or
Yeah, it just goes on by itself.
just goes on by itself? I mean, I guess there's still other probes up there that they sent up in the 70s and 80s and 90s that are still poking around
Voyager
space
1
somewhere.
is the one that's furthest out. Voyager 2 is next in line. Voyager 1 is halfway out to the Oort cloud, I believe.
Yeah, that's exciting.
So that's getting way out.
So I guess what I'm asking is that they don't expect much from it. After it's done its job, eventually it just stops sending things back, and they say, okay, that's that.
Yeah, there's no recovery of it.
Right. I didn't expect it to come
Not
back
going to bring
to
it
Earth,
back. The
but,
same with the Voyagers. They just keep on going.
Yeah, they don't have a final destination for it in
And
mind.
it's just amazing that they still can transmit back over that vast distance.
Yeah. Well, I'm hoping we do get some good pictures of things that are in the Kuiper Belt or some of the other dwarf planets, because I liked that Pluto was a planet when I was little, and I want to see what kind of things have demoted it. I remember reading about what the International Astronomical Union had, the terms they'd come up with to classify a planet, and one of them was, it has to clear its neighborhood.
It didn't clear its neighborhood.
And what does that mean?
It means like the Earth, as it spins around the sun, it's not going to encounter any asteroids anymore in going through that path. It's cleared them all out. The only ones that hit the Earth now are coming from elsewhere. They're coming in from the asteroid belt, coming in from out, the Kuiper belt could come in too. Even from the Oort cloud, you could have something coming in from the Oort cloud.
Is the Oort cloud a part of the Kuiper belt?
Oh, no.
That's the next.
Way out.
That's the next phase.
And much larger than the Kuiper belt.
Is it just a cloud of gas?
No, all particles.
All particles?
Ice particles and good-sized particles probably out there too.
Okay. And it's amazing how much bigger our solar system has gotten since I studied it in 3rd grade when the universe ended at Pluto, you know.
Yeah, if you consider the Oort cloud part of the solar system, yes, it's much larger.
Yeah, much larger than Pluto, but now, you know, I think it's Hubble that's detected it, or other instruments that they have stating that every star out there has probably a system of planets of its own, and they've detected that through various different...
Yeah, well, Hubble has given us pretty pictures of stars and gas clouds, things of that nature. But what they did in order to examine planets around stars is they sent up Kepler.
Okay, Kepler.
Kepler is a special kind of a telescope. It doesn't take pictures. Instead, it looks for points of light and just detects those points of light. And it's going for over 150,000 points of light. Those stars that are out there, just like little points.
Right.
And the intensity of the light will vary with time, and that's what they're measuring. They can measure it down to 1 part in 10,000.
That's amazing.
And when you get down that far, you could find that the light from that star is dimming by the amount of an Earth-sized planet going around in an Earth-type orbit, a size orbit, around a sun similar to ours.
And can't they also detect the wobble of that dot of light because of the gravity that specific star is tugging
Kepler.
on it? Is that what they call the wobble?
Yeah, the wobble is detected by, well, you could do it with Hubble, I believe, but mainly on the Earth. We have the Earth telescopes have very sophisticated detection capability, and they'll watch the spectral of the light of the star, and they'll see it change a little bit. And that's what they can detect. Oh, it's changing its frequency. It means it's moving towards us or away from us. What's going to cause it to wobble? Things going around it.
Its own satellites.
So they can use that to confirm what Kepler is finding. Kepler says, oh, there's this star out there. It's got a whole bunch of planets around it. And this is the period of the planets, and this is what you're going to find out there. And then they can take the Earth-based telescopes and look for that wobble around that planet and confirm.
Yeah. And that's just amazing because, like I said, in kindergarten when they insisted that the solar system ended at Pluto and we're it, that's it.
No,
and now I'm happy that they're at least admitting, because it's only logical when you look at all those stars up there and you realize there has to be other planets.
Well, just our Milky Way, 100 billion stars.
I know, it's just absolutely mind-boggling.
And then you look at the universe that we can see, 100 billion galaxies like the Milky Way. Holy cow. Yeah, we start multiplying those two numbers together.
We very quickly start feeling incredibly
look what they got up on the screen now.
So that's what you were talking about with Pluto and his moon.
This is Pluto being surrounded by its moon Charon. Now Charon is close enough to Pluto and heavy enough to move Pluto around. See how Pluto's moving around? Those two guys are actually moving around a center of gravity or a center of mass of those two objects, and that's why you see Pluto going around in a little circle.
And that ties into a little bit of what you were just saying, if it helps people visualize that the Kepler, or I should say, well, as you said, that the Hubble can detect these little dots tugging on its home base planet, I guess, if you will, and detecting that sort of spectral movement when you have a smaller moon or planet circling another planet or star. I guess that's what they use to
detect. Even our sun is moving.
Yeah, it's moving.
Earth is moving the sun. Not much, but enough so that it could be detected by some other civilization out there in space.
And of course, this is all boils down to gravity.
Gravity
Perfect
is doing
lead-in to what we also wanted to talk about today.
Yeah.
Because gravity still exists in the vacuum of space.
Yes, it does.
And
There's
it's
no
kind
limit
of holding
to
it all together out there, isn't it?
Gravity has no limit to its extent. And I was just doing some fancy calculations on what kind of gravity effect is there at Earth by the sun. And it's very, very small. Compared to the gravity here on Earth, it's about 0.3 zeros and a 6. That's tiny.
Right.
And I says, gee, I wonder how that would affect the spaceship that we shot up. And I figured out, well, it slows it down a little bit, but it's so tiny it can't do much. But it keeps on doing it. It keeps pulling and pulling. It accelerates and accelerates. And pretty soon you build up to a very large number, almost 500,000 miles per hour. That is a big number. That's bigger than the spaceship that we sent up. In other words, if you sent our spaceship directly away from the sun on a radial path, it would go out and be stopped by the gravity of the sun and reverse itself and start coming back towards the sun.
Amazing.
Yeah.
And the only thing that can destroy gravity is a black hole, correct? Black hole swallows up even gravity itself, right? Well, I guess, or it has to. I'm not explaining
Gravity
this right.
is certainly involved.
I should say that I should start by asking you that gravity is directly related to mass, correct?
Yes.
So the more mass something has,
If you have,
the more gravity it commands.
that is greater attraction,
Right.
a gravitational attraction by the mass. So if you've got two objects, if there's a very large object, the small guy is attracted to the big guy.
So the fact that my wife is a little smaller than me, and I'm here, I could actually say that she actually is attracted to me because
yes, definitely
I'm
attracted.
displacing more gravity around myself than she is.
I don't know about displacing it, but there's a force between the two of you.
Right.
You can't measure it. Very difficult to
It
measure
certainly
that
is
small amount.
minimal compared to the gravitational differences between the Earth and the Sun, which is why we're in rotation around the Sun. Yeah.
But because we fire out this spaceship tangentially to our orbit, the force of gravity is just causing it to curve. So it curved around past Mercury, and then past Jupiter, and now Jupiter's gravity caused the spaceship to speed up. Picked up an extra 9,000
like a
miles per
slingshot
hour.
technique or something.
Slingshot,
like
they call it,
Yeah, the slingshot technique.
So that helped it to get out to Pluto sooner. Cut off, I think it was about 2 years in the trip. It was a 9-year trip. It would have been 11 years.
Could be a handy thing. Why don't we backpedal a little bit and explain as best we can what makes gravity happen?
Well, that's a toughie.
Yeah.
It's just a known force between masses.
Yeah.
Newton first said that, he says, what's going on here is objects attract one another. And from that came his 3 laws. He says, these pieces of matter will say they have mass. And that mass has a tendency, if you start it going, it'll keep going unless another force is on it to stop it. If you put more force behind it, it just keeps going faster. If you put a force on the other side, it slows it down. Okay. The other thing that he said, that if you've got a force on this object, it will accelerate. So not only does mass continue to go unless you put a force on it, but the force you put on it accelerates it. That means it goes faster and faster and faster. Well, pretty soon, there's a limit to it. If the force you put on it equals the force that forces back by the mass, you have equilibrium. And that's what happens with the orbits. You're forcing that planet to go around in a curve. It wants to go straight. It can't go straight because gravity is pulling it around into an orbit. if it pulls just enough that the force on there, because of the acceleration times the mass is the force that's there.
Right.
You're pulling on it with gravity. When the gravity force equals the acceleration force, then you get a stable orbit. And that's where all the planets go in a circle.
F equals ma. I remember my physics teacher
F equals ma. The force equals the mass times the acceleration.
Yeah. My physics teacher just banging that into my head in high school. I just remember that. And gravity has a lot of mysterious properties about it. Like, why is it that something with more gravity, time slows down around it?
I can't explain it.
I don't know if a lot of people can explain it, but gosh, it's a proven fact. It's absolutely amazing.
It's something that you can prove, yes. And so we have satellites up in the sky, and those satellites are what we use for GPS. GPS is what we can use to navigate around our streets and guide us. We don't use maps anymore. We have a little GPS device in our car, and we follow the GPS device. Well, in order to do that, you have to have exact timing. But the timing changes when you go up into a satellite because you're further away from the gravity of the Earth. You come near the Earth, you got slower time. So the time down here is slower than the time up there where the satellite is. Sort of amazing, but it's part of it.
So they're constantly recalibrating the clock
We
and the satellite.
have to take that into account. The other thing that's going on is the satellite's going pretty fast. And the faster you go, the slower time goes. So time is slowing down because the satellite's going fast, and time is speeding up because it's away from the gravity. And so we have to do both of those.
See, I'm about to tell Diane we don't need to get a time code generator for our control room. We just need to put more gravity over in there. So all of our clocks are
Sorry,
on
you can't do that.
The same second. I guess we should just put some more mass over there or something. I don't know.
Yeah.
But it's interesting. I think I read I think this was in high school physics class, an experiment that I think Einstein did. I think he put a clock on the top of a skyscraper. I think it was the Empire State Building. And he put one on the bottom, and he let it go for a week or a month or something. And the clock at the top of the building was a few seconds ahead of...
That was a hypothesis.
Was it a hypothesis?
Yes. Okay. To illustrate what he was talking about. The difference is so small you can't measure it.
Right.
Okay. But when you put a satellite there, now you can measure it.
The satellite story you told certainly illustrates. Certainly illustrates what we do. I remember the best example, I shared this with you before the show, the best example that was ever explained to me about how gravity works was when my teacher took a cloth napkin and he had us pull it tight so it was straight out, and he took a marble and he put it on the cloth napkin, and it pressed down in the napkin a little bit, put a little dent in it. And then he took a heavier ball, like I think it was maybe even a bowling ball, put that in the cloth napkin, and that sunk it down real quick.
Right.
And the marble rolled towards the bowling ball.
Right.
And he said that in space, there's no friction. So the acceleration gained from that marble being attracted to the bowling ball, because it, created a downward compression on the cloth napkin, would just cause the marble to keep circling around it if this was a vacuum without friction. And so that is what really made it click for me.
What Einstein was talking about as the deformation of space-time.
Right.
And that is a hard one to think about.
We start to get a little abstract if we start talking about space-time, but essentially my teacher said that if the cloth napkin, if we could actually see it, that's sort of what's happening in space. There is this fabric that we cannot see, and it's sort of bending it. Things that have more mass are putting a more heavier compression into this space-time
Since
fabric.
Einstein was a mathematician, he visualizes things such as that.
Yeah.
He sees his equations saying, this really looks like a fabric.
Right.
And the fabric is getting bent by gravity. And that's a very wild concept, okay? Right. But all his predictions are coming true, so we have to accept the equations that he came out with. Okay?
And I guess if we're going to talk about a black hole, since I brought it up before, correct me if I'm wrong, a black hole is
very deep
massive
depression.
object of whatever it did, and instead of being held and compressing the napkin, it tore through it. Because it was so massive, it tore through it, and it's causing everything to fall into it, even light. And I guess there's just so much gravity around a black hole. That's why it's sucking.
Yeah, the
things
gravity is so great that even light can't escape it.
Yeah, which is kind of scary at the same time, but I think it...
But they are real.
Oh, absolutely.
There's a black hole holding our Milky Way galaxy
Oh, you
together.
beat me to it. I was going to say the spiral galaxies that we see out there on telescopes are
Yeah,
a black
they're
hole.
finding black holes in the center of all of them.
Right. And it's I guess, what, in hundreds of billions and trillions of years, it will eventually suck up our galaxy, but that's so far away. It's at least giving it its shape that we see right now.
Okay, I hadn't seen any predictions on it.
That's why I made up a big enough number that was...
No, you don't have to worry about that one.
Absolutely not. No.
Not in our lifetime.
But I did know that at the center of most of those spiral galaxies, there's a black hole. Yeah.
A massive black hole. There are smaller black holes too. When a star collapses, that's a very large star, it can collapse into a black hole. Whereas these massive black holes are so much bigger that they can constrict all the stars in a galaxy. So very big.
And if anybody wants to see what it's like to go inside of a black hole, they can see the science fiction movie Interstellar that came out last November. I don't know if people can sit through that long of a movie, but they do take a few liberties and show what it's like to fly into a black hole. Looks like Diane's got a black hole up there for us on the computer.
Okay.
An image of one.
I'm not sure how that relates to a black hole, but so be it.
It's given the idea of things being sucked towards the center.
Well, see, as the black hole is attracting things, they start spinning around like in an orbit around it. And unless it gets sucked into the black hole, it'll just keep spinning at a very high rate around the black hole.
And so that makes sense. The black hole is essentially generating most of the energy in the solar systems, or the galaxies. Is that a good way of looking at it?
I would not really relate to that.
Oh, okay. I don't know. I was asking. So,
now, there's no energy coming from it. It's when you have any particles in space, if they are moving at the very same velocity together, well, then gravity would bring them together, and they'll collide. But if one is going faster than the other, it will start to circulate. The two guys will go around one another because this guy is going forward, but he's being attracted in. So he's sort of starting around a circle. And it just keeps on going around. He gets around to this point. Well, that's like he was over here. If it went around 1/4 of a circle, it'll go around the other quarter. Gets there, it's the same situation. It'll get around to this quarter, and it's the same situation, get back to where it started.
yeah.
And so any particles in space, that's why you see stars going around the black hole of the galaxy, why you see the planets going around suns. It's all because of the same concept. Things that are not going at the same velocity will tend to circle around one another.
Okay.
And that's what we just saw with Charon going around Pluto.
I guess that's kind of what I meant with the black hole being at the center of a galaxy. It's helping generate some of that movement that you were talking about.
It certainly generates the movement. That's not generating energy.
No, yes. Yeah, I guess
You're not creating energy.
I misspoke.
Yeah.
So is gravity also what makes things spherical? The planet's spherical.
Yeah. The Oort cloud is not a disk such as our solar system. The Oort cloud is a sphere. And that makes a lot of sense because it's the same force in all directions.
Gotcha.
So you got a sphere. It's very symmetrical, no matter how you look at it. And the Kuiper belt, however, I think that's more like the solar system. It has collapsed into a disk. I don't think that is spherical. The planets, of course, are in a disk. Pluto is a little exception. It's a slanted orbit.
There's Pluto.
Yeah. Hey, yeah, that's a close-up of Pluto.
That's one of the new images released.
That was taken
Horizons.
just a few days ago, I think.
Yeah, that's one of the newest ones that just came out with the famous heart.
Yeah, they point down the lower right-hand corner is a heart, great big heart. And as we get closer, we'll find out more about that.
Well, back here on Earth, we're out of time.
Okay.
And so I appreciate you coming on. It's always fun talking to you.
Yeah.
Time flew by as usual. So maybe till next time we'll have more exciting updates about the New Horizons and we can have you back. Okay?
Sure. And anybody interested in cosmology, they can come out in September.
Great.
September, the second Wednesday of September. And we always meet on the second Wednesday of a month, every other month. So it's the odd months, 9, 11, and so on. And we meet at Town Center in the music room at 2 o'clock on the second Wednesday of those odd months.
So if you want to hear more about New Horizons and Curiosity Rover and Gravity, you can always check out Richard and his group in the Town Center music room. So we'll see you later, Green Spring. Thank you for watching.